2.3 notes, organizing quantitative data. The goal today is to be able to organize using histograms, dot plots, and stem and leaf diagrams to organize quantitative data. 3 things. Group observations into classes. So that's a new term. We're talking about each one of these rows in our frequency or relative frequency distribution. That is considered a class. So we treat the classes as the distinct values, just like we did when we did qualitative. So values of qualitative truly goes in this blank. And then that next step is to construct our frequency and relative frequency distributions in the same way as we did with qualitative data. Truly goes in that blank as well. Next we have these 3 common sense guidelines. When you think about it, they make sense, but sometimes we forget to think about it. So these 3 common sense guidelines for grouping our quantitative data are: the number of classes should be between 5 and 20. You don't want to have 50 classes. That no longer even feels like it organizes the data for us to be able to analyze and interpret all that well. The second thing is each observation must belong to exactly one class. And lastly, all classes should have the same width. So here's an example of classes having the same width. If I go from 0 to 4, 5 to 9, 10 to 14, and so on, each one of those classes has a width of 5. 0, 1, 2, 3, 4. 5, 6, 7, 8, 9. So if you did something like this, where we did 0 to 5, 5 to 10, 10 to 20, that breaks both of my rules. 0 to 5, 5 to 10, those are the same length, but 10 to 20 is a larger width. So that does not qualify as meeting the 3 common sense guidelines. The other thing is, what if I have the number 5 in my data set? It would land in 2 different categories, so you can't have that. Let me get that piece. That's just a little reminder. This comes up quite a bit where we forget these common sense guidelines. Next, we just have 3 basic methods for groupings, again, so we can stay in line with our organizing piece for our frequency and relative frequency distributions. First is single value grouping. Each class represents a single possible value. For example, the number of TV sets in each of 50 randomly selected households. You have this random data set that's now been organized into a frequency and relative frequency distribution. You can see number of TVs, we only have 0 to 6 in our data set. So check, we meet that guideline of staying between 5 and 20 classes. We have 7 classes in this case. And then we treat it in the exact same way we did with our qualitative data from yesterday. right? We just list out how many people had 0 TVs in their home, 1 person, all the way up to 6 TVs. Wonder how many TVs you have in your house. Where would you fall in this? Tell the person next to you where you would fall. Think about it. How many TVs do you have in your house? It's interesting. I feel like it would change now because I would include iPads. Some people, does anybody just sit and watch an iPad or sit and watch your phone instead of a TV? Anybody in the 0 category? 0 TVs. Anyone? Just raise your hand. 1, 2, 3, 4,
More than 3 TVs in your house?
5, 6. How many? 9? You're off the charts. That's awesome. Okay, so where were you at? Where were you at, Evan? 1. You're in the 1 category. Great. Okay, so limit grouping then is just slightly different because each class consists of a range of values. We're simply giving names to things we're already familiar with. We're familiar with seeing a frequency distribution where we have a range of values. Yes, nod your heads if you agree. You're used to seeing this kind of thing. We're just giving that particular name called limit grouping. Days to maturity, this is talking about investments. In this case, the tally was done to help with going through and saying, okay, 70, where does that one fall? Put a tally, right? You can imagine if I made you do this process, it would take a couple minutes. Totally fine. And then we have some terms that go with this, lower class limit. That's the smallest value that could go in a class. So with a 30 to 39, 30 is the lowest value you could put in that class. Upper class limit is the largest value that could go in a class. Fairly straightforward. Class width, that's just how many, the difference between the lower limit of a class and the lower limit of the next class. So if I subtract 40 minus 30, that's 10. The length of the class is 10. And this one doesn't come up all that much. Class mark, average of the 2 class limits of a class. Don't worry about that one. We'll just cross that one out. Class mark. I feel like that could add confusion unnecessarily. This is the final way to organize one of these frequency distributions. This is just like the last one, only we'll use this one when we're dealing with decimal values or continuous quantitative data. So again, we have some terminology. We're going to cross off that last one, class midpoint. We just don't need to add the confusion. We have the lower class cut point and the upper class cut point and the class width again. The key difference between this one and the last one is just that you will see 120 to under 140, because that could be 139.99999, right? When we're dealing with continuous data, we need to account for those values that come really close to 140, but don't quite get there. Does that make sense? So like 149.9, if we just had a 120 to 140, and then 141 and so on, and we were using limit grouping, we would have no space for these numbers with decimal points. So now we do. That's called cut point grouping, and if you just think about, that's the one with the decimals. We should be good. And we're using the word to under. 3 methods for displaying quantitative data. Kind of gave reference to this at the beginning. The first one is histograms. It's just like a bar chart, but to distinguish between the two, we keep the bars separate. Or sorry, we keep the bars touching on this one. So 2 ways to display the data in a histogram about the TVs, the number of TVs per household. Notice these 2 lines right here indicate that that corner mark is not at 0, 0. Rather, 0 starts over 1. That's not the standard, so whenever it's not the standard, typically the standard is that this value at the intersection of x and y is 0, 0. But since 0 doesn't start until over here, where 1 would typically be, we put those 2 lines in place. We're not at a spot where you'll have to be generating your own graphs yet, so I think that once you see this, you'll see this a few more times, and just identifying the correct graph and things. We'll talk more about misleading graphs in 2.5. So that's just like a sneak preview of what's to come. In this next example, the limit grouping, you can see the difference here in the histograms. Whereas when you were using single value grouping, the value was right in the middle of the bar, right, for 1 and 2, versus over here, where we have the limit grouping, it would be the same with cut point grouping. We have the range, where the bar is between the 30 and the 40. So those are the two types of examples of histograms. Next is dot plots, which is just a graph in which each observation is plotted as a dot at an appropriate place above a horizontal axis. Observations having equal values are stacked vertically, especially useful to compare the relative positions of the data in 2 or more data sets. Just look at those boards in the back of the room. We have examples of dot plots.
So, is this a graph or like, hold on, I'm confused.
It's a display of data, so we call it a dot plot. A dot plot is just that horizontal axis where, for example, if we're talking about people, the number of TVs in households, let's do this one more time. 0, nobody had 0, 1 person had 1, I have 2. Does anybody else have 2 TVs? 3? 4? 1, 2, 3? Okay. 1, 2, 3, 4. Sorry, I'm running into my words there. 5 TVs. 2. 6 TVs. 7 TVs. 8 TVs. 9 TVs. 2, man. Okay, so that's just an example of a dot plot. It's a quick way to display data. Last one is the stem and leaf diagram. So this is the one that's new for some of you. So for me, I looked into why this one came about and what the value of it is. It's to me, it's a little bit unusual, so I felt like I was curious. So here's what I found. It was developed in the 1960s by Professor John Turkey of Princeton University, and it really is pretty genius way to display data. It's easier than constructing a frequency distribution. So it's easier than creating these guys right here. It is just a general display with more information, including both individual observations at the same time as displaying ranges of data. We've got 4 steps to construct a stem and leaf diagram. The first one, can you read that one for us, Grace?
Think of each observation as a stem, consisting of all but the rightmost digit and a leaf and the rightmost digit.
And in a leaf, oh, you read that, okay. A leaf is just the rightmost digit. So we can take any number and we could put it into this format. If I have the number 12, the rightmost digit, every time, the rightmost digit is the what? That's right, it's the leaf. Everything else is the what? The stem. You can see stems would go to the left of this vertical line, leaves would go to the right. If I have a number like 347, the rightmost digit is 7, which is going to be the leaf. Then the stem is everything else. Is it? Will you check? Thanks. Nobody else is letting out yet, but you're probably right. Okay, well,
It says so anyway.
okay, we'll just wrap up these last 2 examples. You can see how the stems work to the left. So in this set of data here, you've got 36. I'm looking for all the 30s just to sort those out into this display. Thank you. I see a 36, so you got that 6 there. I see a 38. You've got an 8 there. And then there's a 39. Somewhere in here. I'm over.
The last row, second. Under 65.
Thank you. I'm looking right at it. So you've got all of these with the stem of 3 and the leaves are 8, 6, and 9. You do want to put those in order. This is the final display right here. There you go. Have a great rest of your day.
Don't forget to like.